Hello, my dear students. Warm welcome to all of you. We are with physics now. Okay, we'll be talking very seriously about physics now. Okay, myself is Dr. Shobboshachi Shen. I'll be offering you the physics courses, course objective, course outcome. You can see on the screen, and we are in outcome-based education. So every course is mapped with what is its probable outcomes, which I have illustrated later on. Now there are 5 modules. Now we'll be adapting one by one to each module and explore the world of physics. Now let us explore what is the topic of the day. You should keep one thing in mind, that whatever we teach in these classes, each video lecture is basically a building block of your future engineering courses. Each class is going to give you some fundamentals, some new concept. And if you add all those concepts at the end of the semester, you will get the correct path of entering into your own engineering curriculum, because all your curriculum are essentially the application of physics. Engineering means physics applications. So let us explore it a bit more. Hi guys, good morning and welcome to my class of Physics 1. We are now a bit busy with the light waves nowadays. Okay, as you know, my last two lecture I actually concentrated on topic about the variety of the electromagnetic waves. Okay, last few lectures we focused on lasers, how it passes through the fiber called optical fiber. It's the applications of laser, application of optical fibers in modern communication system. Everything we discussed. Okay, so basically we are now a bit classical, as I mentioned. We are talking about two very old physical phenomena, but they're very pertinent, very important, because many events that is going to take place, or many physical process that you'll be learning in future semesters. In most of the cases, you'll find out the application of these two events. Okay, one of them is interference, which we have started learning in the last lecture. That is the superposition of electromagnetic waves, and another is the bending of light. That is a diffraction. If you have got is a CD, old day CD, if you put it under sun, you see, if you put it under light, you would see it becomes colorful because of diffraction. So many good things happen, many notable observations are there. Okay, so now we'll actually continue our discussions on interference a bit. Okay, what is interference of light? Okay, we'll discuss a bit now. We have already highlighted what is interference of light, so we are now going to continue with our discussion. Okay, now if you look at the flow of the description, this is the 23rd lecture in the flow for this first year courses, and that is my contact. You can always contact me in those numbers. Now this is something common. We are talking about light waves, which is, at the end of the day, it's an electromagnetic wave, and we are only talking about the visible spectrum, when we'll be learning both interference and diffraction. This is another important parameter for the study, that is the any wave, as a matter of fact, is defined by this parameter called wavelength, defined by the parameter say wavelength. Wavelength is the separation between 2 points having same phase. So this point and this point, this point and this point, so it is lambda. So if we compare these two, so this is wave, blue wave and red wave. If you compare them, you can see actually this is pink. Okay, this is at zero, this is at zero, but this is becoming zero at pi by 2. So there exists a, then we say there is a phase difference of pi by 2. So phase is another term apart from wavelength and frequency that characterizes waves. Phase is true not true for two or more than two waves. So how they are connected, that is described by the phase. And total wavelength is refers to a phase of 2 pi radians. So basically a pi by 2 phase shift will refers to a wavelength of lambda by 4. And this is another important idea. Okay, and this is a wavelength term you can see, and this is when frequency becomes high or low, how the wavelength changes. These things are discussed. This is superposition of waves, that is the basic fundamental phenomena that taking place behind interference, where which is where two or more waves are mixed together. Okay, and so in the study of this interference, these are the very common ideas. For getting interference, the most important point is to know the concept of coherent sources. Coherent source means a wave, the source of radiation, which is going to produce the source of light, which is going to produce light wave having fixed phase difference. Okay, phase difference will be fixed, and the light wave having fixed wavelength. So those type of waves are called coherent. Coherent may be spatial, coherent may be temporal. That is whether the phase difference is fixed over a time or length. That is called coherent source. And superposition principle is another beautiful idea, which is the superposition of two or more than two participating waves, and interference is the redistribution of intensity due to the superposition of waves that I discussed in front of you in previous classes. Now please look at the picture. It's a beautiful picture. This is deciphering the interference phenomena. Here, waves are of same phase. Okay, this you see this and this same phase. Okay, if the phase difference is zero, then the results in constructive interference. And here you see this is at maxima and this is at minima. Okay, this is at maxima, this is at minima. Okay, this is at minima. So what is the phase difference? If one of them is at maxima, another is at minima, half of the wavelength, that is phase difference, is pi. Okay, that leads to destructive interference. Okay, so phase difference is pi. Pi is the phase difference. And lambda by 2 is the path difference. For constructive interference, you see the intensity is growing. In this case, amplitude is growing. You can see ultimately intensity is proportional to amplitude squared, so it will go up. And for destructive interference, the final intensity because of superposition will be dropping down. Okay. Well, this is the interference due to the division of a front. Source of light, you can see these are the this initial wavefront has been divided. This will be the source S1, this will be the source S2, and ultimately they are interfering with each other. Okay, as you can see there, you see from the source S1 the light is coming here, from the source S2 it is coming here, and ultimately they superpose with each other and giving an interference pattern like this. This is S1, you see this is like S1 and this is like S2. And you see from S1 and S2, whoever is coming, they are actually now superposing with each other, and because of that you get a interference pattern. Okay, because of that superposition phenomena, if you experienced it, because of superposition phenomena, okay, you can see interference is taking place. Okay, now what I did the other day, The interference. This is the interference or division of wavefront. This is one class of interference where the initial wave is divided into two parts. Into wave from the source there is divided into two small short sources of S1 and S2. So that because of Huygens principle, initial wave has been divided. Wavefront has been divided. So this is division of wavefront. Another type of interference can take place. There is a division of amplitude that you can see here. This is used in Michelson's interferometer. Okay, you can see the initial intensity here. It is coming. A portion is transmitted to the glass, and a portion is reflected here, and so on. Okay, like this. So basically, if the initial intensity is I, you are dividing the intensity into parts. If it is I1, this will be I2, like this. Okay. So basically, in this way, this whole phenomena take place. That the initial intensity, this is what is coming. Okay, it is divided into parts. So this type of interference is called the division of interference or division of amplitude. Okay, because initial intensity is proportional to amplitude square. So what you are dividing the amplitude into parts. Okay, because of through reflection and refraction. Okay, you can see two beams are there. Okay, the moment it is incident here, a portion gets reflected, a portion gets transmitted, and this is also the transmitted beam. So if this intensity may be something like say I3, okay. Now the beam, this is a mirror. From this mirror, the reflected beam will be transmitted to the glass. So you get another radiation of intensity, say I4. So I3 and I4, they will actually superpose with each other, and because of that, you'll get a interference pattern. Okay. So because of that superposition, so what is happening? Initial intensity, you see, it is being divided into parts. So that's why this is called the interference by division of amplitude. So earlier one was young interference by division of wavefront because here the initial wave pattern. Okay, and this is interference by division of amplitude. So this is division of wavefront. You can see in the picture also. Initial waveform is separate. Okay, it is divided. Okay. So this is division of our font, and just beneath this you get the division of amplitude. So to make a summary is that intensity distribution, okay, due to the superposition of this interference, intensity can grow called constructive interference, intensity can drop called destructive interference, and apart from that also, okay, because of because the interference can make up two more classes. The interference of the initial wavefront is divided, that is called interference or division of wavefront, and the other one is that interference or initial wavefront is amplitude, it gets divided, that is interference or division of amplitude. Okay, now this is famous Young's double slit experiment, which is the example of interference by division of wavefront. So after at the end of this class today, we will also talk about another experiment where interference will take place because of division of amplitude. The name of the experiment is Newton's ring. Okay. Now here you can see it's a very popular experiment, the Young's double slit experiment.
বাবা
Hmm.
বাবা কালকে দিদি ওরা আমার জন্য কিনে দেবে আমার হলো ডাইনোসর আছে দিদি হলো বারবি আছে
So now you can see this is a source of light. So these are the two secondary sources. This is one of the secondary source. This is another secondary source. So this initial wavefront, you see, this is the initial wavefront. This has been divided. So it has been divided into parts, and ultimately these divided wavefronts are actually meeting with each here and giving this interference pattern. These are the bright and dark fringes as it is written there. You can see. So ultimately, it is interference distribution of wavefront that we discussed last day. This figure I actually shared you last week also. That if these are my two sources, S1 and S2, separated by length say R, and separation between the two slits is D, then at the point P, what would happen? The whether there will be getting, you will get constructive interference or destructive interference. that depends on the phase difference between these two. So phase difference depends on the path difference. What is the path difference? Path difference is this much. If you look at the picture, you see two waves have not started together. Then this wave is always a bit, okay. So you can see here. So these are the two sources, one and x2. So basically, this wave starts here and this wave starts here. So there is a path. You see, if you drop a normal here, this is the path difference. Okay. So it becomes d sine theta. Sine. So you see, for constructive interference, it should be multiple of lambda, even multiple of lambda by 2, so it is n lambda. For destructive interference, odd multiple of lambda by 2, you can see that. Okay. So now this path difference is d sine theta is equal to n lambda. So d sine theta equal to n plus half lambda. Okay, and separation between the gap between the two fringes is given there. Okay, for small theta, but I'll show you some more calculation. That is, if the participating wave, I told you that those things in the last day also, if one of the participating wave is a1 sine omega t and the other one is slightly maintaining a phase difference of phi, okay, if they superposes, okay, if they superposes, if this to him, so it's like sine, okay, plus b type of quantity. So if they superposes, this is like this one, a1 sine omega t, a2 sine omega t plus phi, okay, that is taking care of the phase difference. So now in that sine omega t plus phi formula, if you do the expansion, it will become, you can see there a1 sine omega t, a2 sine omega t plus phi. If you do the expansion, it is like y a1 plus a2 cos phi sine omega t plus a2 sine phi cos omega t, okay. So therefore, if you look at this expression, you see this is, if you take the it common sine omega cos omega t or cos phi omega t, it is like a1 plus a2 okay, cos phi sine omega t, because I am keeping this sine omega t terms together. Okay, sine omega t, and on the other side a2 sine phi cos omega t. Now let us assume that a1 plus a2 cos phi is equal to capital A sine theta and a2 sine phi is equal to capital A. The first one is cos theta, second one is sine theta. If you put the values, it is like this value of, so it will become a1 plus a2 cos phi created as cos theta. Cos theta is sine phi is equal to sine theta. So it becomes equal to a1. If we square it, you see it will be, if you square this equation, they're adding This will give you the value of phi. A plus b whole square plus b square. So now this quantity a1 square plus a2 square cos square phi a2 square cos square phi a2 square sin square phi make it 1. So it is a1 square plus a2 square and that 2ab term. Okay. Uh, is equal to, if you compare to the other side, it is a square. Okay. So let us consider this. This is like a1 square plus a2 square plus 2 a1 a2. You see, because it looks like this much. A cos theta plus sin omega t, a sin theta plus sin cos omega t. So we have to a mixture of everything, the theta term, the initial case, and the angular term. Okay. So you can see there. So this will make, this is the mini intensity. You can see there a1 square plus a2 square minus 2a1 a2 because of the cos. Okay. For minimum, you see this cos phi term has to be 1. So this is like a1 minus a2 square. Okay. So high minimum is, you can see there, a1 square minus plus a2 square minus 2x a1 a2 will be there, but it is less than the individual amplitude square. And phase difference is 2 pi by lambda into path difference. So this gives 2, that must 2n plus 1 lambda by 2. For getting very good contrast in the picture, okay, a1 should be equal to a2. So this I will be equal to 4 square. Okay. So basically it is becoming I max equal to 4 square and I mean equal to 0. So intensity is 4 times, which you can see from here also possibly. Okay. So the maximum intensity is like, as you can see there, I maximum is equal to 4 square. Oh, sorry, I missed this. For maximum intensity, you see, for maximum intensity, cos theta should be equal to 1. Because if this is 0, then everything is a big 0. Phi with 2 and pi. So basically, if it is 1, it is 1 plus it is whole square. You can see it clearly, it is quite crystal clear from the picture. So the corresponding phase difference is 2 pi by lambda into path difference. Okay. And now here you have to put the path difference. If it is n lambda, n cancels. So phase difference is becoming 2n pi. Okay. For minimum intensity, this is something I already discussed that because of that minus sign you can see, and I minimum is like a1 square plus a2 square. Phase difference is 2 pi by lambda into path difference if you put the value, and for good contrast is both is it the same. Okay. Now let me calculate average intensity. A1 equal to A2 means like 4 square. Now average intensity means over the entire I d phi, average over the full cycle. So I is this much. Okay, is obtained from this page. Okay, so if you see here, if you do the integration, A2 square phi or square phi. So you can see here, you put the limits 0, sine 0, 0, sine 2 pi is also 0. So slowly, by it is reducing to a formula. Okay, so average intensity as you can see here will be like 2 square. Okay, maximum intensity is 4 square, minimum intensity is 0. So average is averaged out 2 square. Okay, so there is no loss or gain of intensity. Okay, now condition of sustained difference, you need coherent sources. Sources must be narrow, otherwise it will act as a multiple source. The sources should have the coherent means their wavelength should be same, frequency should be same. They should maintain either no phase difference or a fixed phase difference. The amplitude of the two waves should be equal so that you can get good contrast between the bright and dark fringes. The distance between two sources should be small. The distance between the source and the screen should be reasonable. So that condition approximation to the large case you can do. Okay. Now let us do a small calculation of the fringe width here. You can see the point P. Okay, everything is so much descriptive. You can see 2D is the separation. Okay, it is not like in the last. Okay, it is 2D. Okay, initially we discussed that as by D, but ultimately the path difference is there is 2P minus S1P. Okay, path difference you can see there. So to calculate S2P, you can see there the length vector. Consider delta is N2P. So it becomes, you can see there is 2P means this much. S to N is this, and NP is basically this. So by geometry of the problem, s2p square is equal to d square plus x plus d, because this is x and this is d upwards. So if we apply, if we take the common one plus x plus d by d square to the power minus half, and now if we apply that formula of expansion, okay, binomial expansion, then this takes a form like this: one is half will come in from, and so on. We have kept on the positive sides, okay, because half is also positive. So now what would happen for d too much high, x plus d is compared to x plus d, and
हेलो शेषवीय की करे
therefore higher power term, okay, for a very high d, the d power will be increasing, so will not consider that. So basically we'll talk about only the up to d square. So if you multiply d, so that d is getting in according to your formula x plus 2 square, okay. So you can see there d plus, so you can calculate s1p considering the putting the value s1p in a similar manner, d plus x minus d to be the value. So now x1 s1p, okay, d plus x minus d plus 2d square, which you can see here. S1p is displacement. Uh, this is the origin. This is d. And you can understand this is d, small d. To get the justification, if we use it as a formula, s2p minus s1p, okay, the path difference is this much, 2x d by d if you put the value, and for the nth fringe it is 2xn d by d. Now for bright fringes, this is multiple of n lambda equal to n lambda, so xn equal to d by 2 dn lambda, okay. So xn plus 1 minus xn, as you can see here, dn plus 1 by lambda minus by, so d by 2 dn lambda. So d by 2 dn lambda. So basically, the first term. So these two will cancel, and this is going to be the value. And for dark fringe is also same thing. xn 2n plus 1 d lambda by 40, you can see. So if you subtract it, you will get this value. So to determine the spacing between the, you see the spacing between the two fringes is beta, is therefore is like to the separation between them inversely proportional to the split width like this, okay. Now the other type of system where you can see formed by The interference, the division of amplitude is called Fresnel's prism. It is not in your course, I'm not highlighting. I will talk about Newton's ring. Now, Newton's ring, this is a glass plate. So, from the source, suppose there is a lens system whose focal point is lying here. Okay. So, light ray passing through, what will happen? That it will be focused to this position. From here on, a portion will be reflected inside and a portion will be transmitted through. The one gets reflected inside. What will happen? It suffers. It suffers a reflection from here. It suffers a reflection from here. And ultimately, you see, whenever any radiation is coming in, from this surface there is a reflection. You can see here. So it will go down and a portion is getting inside. So some portion is. So basically, one portion of the beam will be reflected from here. If the initial this intensity is I1, if this is I2, so now it is transmitted through. From here it is reflected. From here it is transmitted through. So final intensity will be less than the is, okay, because of the interference will take place. The path difference between the interfering wave is given there. It is 2 mu t cos r plus theta lambda by 2. Effective path difference is for large radius of curvature or for small angle theta will be reduced to only the cos term. Okay, because theta is small. So for maxima, it is 2 mu t, or mu is the refractive index of the medium, that is glass in this case. It will be 2 mu t plus lambda by 2. This is equal to n lambda, and t is equal to 2n minus 1 lambda by 2. Because if it goes to the other side, okay, 2n lambda, it will be there. And for minima, that you can see here, 2 mu t plus lambda by 2 is equal to 2n plus. This is the condition of first one is constructive interference. Maxima is showing, and is for destructive interference. So the condition would be that you see for maxima, this is the relationship, and for minima, this will be even multiple of lambda. Okay. So why? So central ring means the thickness T is 0. So delta is lambda by 2 means pi phase difference. Okay, so that's why central ring is dark. This is a very important question, this I think. Okay, very important. Okay. Now path difference from dark ring is 2n minus 1 lambda by 2, as you can see. So lambda by 2 means pi phase difference. Okay. Now radius of curvature calculation, etc. There is an experiment inside the lab where this formula is actually used. Okay. You only remember the final formula, which is one. So you can see here, if I replace the t here from this expression, so we get rho n. Okay. So these are moving up, so ultimately rho n square is this much. Rho is this. And for diameter, you can see there dm square, dn square is there. So it is like this much. For dark fringes, the opposite story, it is n lambda. So if you put the value of t, you get this much, n lambda r. Okay. So Pn you get diameter of the, you have obtained 4 n lambda, and so d is proportional to root n. The diameter of the dark is proportional to the square root of the natural numbers. You can see there. And you've got an experiment actually where you have to calculate the wavelength of an unknown light. Okay, this is the formula. So it is dm plus n square, okay, minus dm square, okay, divided by, okay, 4 n r. R is the radius of curvature of the lens. Domination of wavelength of light by Newton's ring method. So this we have got, and this is the formula I was talking about. So this formula will be utilized in lab to calculate the wavelength of the red light. Okay. So thank you for your patience. It has been a very silent journey so far. Next day we move toward diffraction of light. Just a minute. Sometimes problems do appear with this, so it's very important also for the purpose of the okay. So this is actually one of the lab experiments also. So next day we move towards the diffraction of light. Thank you.
You and me were meant to be in the great outdoors, forever free. You and me meant to be in the great outdoors, forever free. tree. I'm just sitting here. I got time, it's clear to see. From up here, the world seems small. We can sit together. It's so beautiful, you and me. We meant to be in the great outdoors, forever free.